Okay, so welcome everybody back for today's second speaker, and we will have the talk on smooth reheating via non-Abelian dark sector by Simona Proracci, and let us begin from University of Geneva. I'll send you a reminder when 5 minutes are left.
Okay, thank you. Yeah, thanks for having me to this interesting series of seminar. And today I'd like to tell you about a project I wrote with Simone Biondini and Elena Koledova. But before I start, let me also tell you that just before we put our project on the archive, a very similar work appeared. So if you find my talk interesting, you also might want to check this reference I put here below. Okay, and now let's get to it, but very slowly, because to expose the questions we try to answer, I like to start with an overview of what we know and what we don't know in cosmology. In particular, I'm interested in the history of our early universe, meaning before the emission of the cosmic microwave background. And there, what we know actually is mostly because of the CMB itself and its features, and also thanks to collider searches that pushed our intuition about 20 orders of magnitude in time backwards. But there are some features in the CMB that we can't describe just within this scenario that has now become standard. And this was the inspiration for some models that might have take place much earlier, about other 20 orders of magnitude earlier in time. And I will just give one example of one of these astonishing features of the CMB. And this is the very famous plot of the spectral correlation of temperature fluctuations on the CMB surface. And on the x-axis, we have frequency. Therefore, if we look at the right, we have large frequencies and so small distances. We are looking at correlations over very small distances, while on the left hand of the left side, we have small frequencies, and therefore what is illustrated here are correlations across very large distances. And the reason why this plot is really amazing, even if we have seen it many times, is because contrary to our expectations from classical statistical physics, what we see here is that we have very large correlation on large distances, while on small distances, we have almost no correlations among the temperature fluctuations. And one way to explain how so strong correlations over large distances might have an origin is the idea that earlier in the past, at some point, the universe was expanding in an accelerated fashion, such that the causal horizon on the CMB surface corresponds to the large distances at which we see a peak in the correlation. So this is what we call inflation in general, this early and short period of exponential expansion. And to describe it, actually, we don't need so many ingredients. So we assume that at even larger scales, the universe is homogeneous and isotropic, and therefore the metric coefficients only depend on time. And this is what I will also assume for the rest of the talk. Then we have A, which denotes the scale factor to measure special distances. And the expansion rate of the universe is the Abel rate, I denote with a H. And at the same time, the energy momentum tensor must then be diagonal. And we assume a generic equation of state that relates the pressure to the energy density. So if we use these ansatz in Einstein, to evaluate Einstein's equation, we obtain the two Friedmann equations. And looking at the second one, we see that an accelerated expansion meaning that A dot dot is positive, requires a negative pressure. And the easiest way to parameterize a negative pressure is to take a scalar field and to have a very large potential energy. If this is the case, not only the pressure is negative, the energy is dominated by the potential. And if the potential is also nearly constant for a while, I think someone is not muted.
Yes, sorry, just give me
Sorry.
a moment. Yes, sorry, please carry.
Okay, sorry. So if we have a self-interaction potential for the inflaton field that at a given time is nearly constant, looking back at the first Riemann equation, we see that also the energy density will be nearly constant, meaning that the expansion rate is constant and the scale factor grows exponentially. So we already see how the dynamics of the scalar field should look like. For a while the potential is dominating, the scalar field evolves very slowly. But at some point, as if the potential has a minimum, the kinetic energy will become again comparable with the potential one. And at that moment, some oscillation will start then around the minimum of the potential. So now let's go back to the big picture and think that, okay, now if we have this scenario at very early times, then if there was another species or a plasma around before and during this inflation period, then afterwards must be completely diluted away unless it couples to the inflaton field. But in the simple scenario we were talking about, at the end of inflation, we are left with an almost empty universe. On the other hand, before we were talking about the very complex and rich environment that sees standard model fields that interact with each other more and more at higher and higher temperatures. So then the question is how this rich environment emerged from the empty universe after inflation, and from what? And this transition period is a fairly unexplored stage in our cosmic history. And this is also what we were really curious to describe. And we decided to do that by addressing another accepted speculation in particle cosmology, which is dark matter. So our idea was quite simple. We place ourselves at the end of inflation and ask what happens if the inflaton field decays very weakly to a dark heat path, so to a dark plasma. And this dark sector itself will then partially decay to standard model degrees of freedom, sourcing the visible sector, and partially remain constant, remain stable to form the dark matter we might observe today. So then if we write the Lagrangian of everything, apart from kinetic terms and self-interaction terms for the different sectors, so the inflaton sector, the dark sector, and the standard model, we then also need some interaction term between the inflaton and the dark sector with a generic dark operator I call J. And we also need some portal interaction between the dark sector and the standard model. And now that we have Lagrangian at hand, we can already also try to guess what are the evolution equations for the energy densities in the different sectors. And in particular, we expect that at the end of inflation, then the there must be some sort of friction that subtracts energy from the inflaton field and um, source or maintain the dark heat path, so as a source term on the right hand side. And at the same time, we also expect the dark sector to decay to the standard model, so we should have a decay rate that again subtracts energy from the dark sector and populates the visible sector. And all of this happens in an expanding universe, so we have the Hubble rate entering the equations, which also dynamically depend on the total energy density. Sorry. And the friction term and the decay rate themselves, they also might be dynamical. So all in all, this set of equations is highly nonlinear and coupled. We cannot solve it analytically, but we can do it numerically. But to solve it numerically, we also need some ansatz, in particular for the dark sector, because having an ansatz, we can then compute or evaluate the friction rate, which depends on the dark operator. The same for the decay width of the dark sector into visible sector depends on the choice of portal interactions, on the choice of the dark sector. And we also need an input for the equation of state of the dark sector. So let me now expose a nice concrete example, which is the one where the dark sector is made of non-Abelian gauge bosons. So why dark vectors? The nice feature of gauge fields, vectors, is that we can, or they can interact with the inflaton field via an axion-like interaction term. And this term presents symmetry under some type of shifts of the inflaton field. And this protects the inflaton potential from perturbative corrections. This is a good news because it means that the inflaton potential is not touched and inflation can take place as usual. We are not affecting that dynamics. At the same time, if the perturbative corrections to the potential are suppressed, what is not suppressed are the effects that lead to a friction, which takes both perturbative contributions at very low temperatures, but at high temperatures, it even takes some non-perturbative contributions. And this is also an important ingredient because it means that our scenario might work and we transfer energy effectively from the inflaton to the dark plasma, no matter how small is this friction term. And then being non-Abelian also has his advantages. In particular, non-Abelian fields are believed to thermalize efficiently with this rate in general. So this simplifies our life because if this is the case, we can assume local thermal equilibrium and parameterize the thermodynamic functions of the dark sector by a temperature parameter. On the other hand, from dimensional transmutation, we also know that for non-Abelian fields, there might exist a scale at which the self-interactions within the dark path become strong. And once this happens, then we need the full non-perturbative information to parameterize the thermodynamics of the dark sector. So this is the thermodynamic functions for non-Abelian SU3 gauge fields are illustrated in this plot using lattice fits. And this is what we see, like we have a critical scale below which we need non-perturbative input, so we need lattice for the parameterization. So also a very convenient fact about non-Abelian gauge fields is the presence of lattice results. So from now on, then I will work with SU3 and use lattice results whenever possible. Okay, but now if there exists this scale, and we see a confinement of our dark sector, what are the physical degrees of freedom after confinement? Well, since I'm not adding any fermions here, below the critical temperature, we will have strongly interacting gluon states, so glue balls. And since vectors carry Lorentz indices, the glue ball states will organize for their tensor structure and therefore have different quantum numbers that we can classify in terms of spin, parity, and charge conjugation signs. And moreover, also for all the global states, we can associate a mass that is proportional to the confinement scale. So the full spectrum in the SU3 case, for example, looks like this. And so we have the mass on the y-axis, and on the x-axis, I'm ordering the sign in parity and charge conjugation. And I drew this line to separate C even global states from C odd states, because the charge conjugation sign is the most important one in our scenario. And it's because C even operators in the dark sector can talk to C even visible operators, so standard model operators, via lower dimensional operators, of course. And the lowest dimensional interaction term we can write in the Lagrangian has dimension 6. This means that the decay with from the dark to the standard model sector for the even states will scale with the confinement scale to the power of 5. The story is different for C odd states, because to talk to visible operators, they need to appear in a composite way. And therefore, the lowest dimensional interaction term we can write has dimension 8, meaning that their decay rate goes as the confinement scale to the 9. And you might already see where I'm going, because then the even states that decay more efficiently to standard model degrees of freedom, they might be good candidates to take the role of sourcing the standard model, while the odd states, maybe they are more stable, so because they have a smaller decay rate, and maybe they are stable enough to remain around until our days and form the dark matter. But yeah, so I was presenting this plot with a few states. In principle, we have a tower of global states, and the full scenario might become a bit complicated to parameterize. So for the first analysis, we start with the first lightest and therefore more abundant global states, which are the 0 plus plus, the 2 plus plus, and then also the first lightest odd state, the 1 plus minus. Good, now we should have more or less all ingredients, and we can go back to our evolution equations. We have said that if we finish inflation at the energy scale, which is higher than the confinement scale in our dark sector, then the dark sector will be deconfined, and which is an easier assumption, since this allows us to assume equilibrium, temperature parameter, and parameterize the equation of state and work out the decay rate. So we are left with the temperature parameter as the variable for the dark sector, and then we have the inflaton energy density and the standard model energy density as further variables. In total, 3 variables for 3 equations. This is good. And the 3 parameters in then in the set of equations will be the confinement scale of the dark sector, and also what I call M, which is the energy scale at which the portal interactions between the visible and the dark sector will happen. In principle, we also have maybe more parameters entering the friction term, but they are settled, they are fixed by the inflation scenario. So we can solve now this system, keeping in mind that whenever the temperature in the dark sector reaches the critical value, we need to stop our evolution and think how to how the equations then will look like in the confinement scale. But let me show you some spoiler of the solution, because of course this is now the example for a good choice of parameters, for a good choice of the confinement scale and the portal energy scale. And then, okay, we look now at energies larger than the critical ones. So we are at temperatures larger than the critical temperature. And the solution really looks like how we would we want it to be. So starting from the blue dotted line, this is the energy density of the inflaton field. It is constant at the beginning during inflation. Then inflation ends, and a very long matter-dominated era starts, which is characterized by this redshift. And in the meanwhile, this red dash curve represents the energy density in the dark sector, which is maintained by the very small friction which exists among the inflaton field and the dark bath. So during inflation, the bath is just maintained. And then we see the bath reaching a maximal temperature just at the end of inflation. And afterwards, the redshift in the dark sector is less steep because we have a radiation-like equation of state. While the orange curve, this is the standard model energy density, which is sourced from the dark sector and behaves very similarly. It has also a very similar equation of state after inflation. So this gray band denotes the moment where we reach the critical temperature in the dark sector, which then undergoes a phase transition. And also it coincides very nicely with the moment of the moment where the inflaton field decays away and it becomes negligible afterwards. But after the phase transition, then, okay, on the one hand, we don't need the first equation for the inflaton field anymore, so we don't need the friction term. This might simplify our life a bit, but we should then think that the dark degrees of freedom, they exit equilibrium because they start interacting strongly among each other. So just after the phase transition, we should enable also our system to capture the freeze out of the global states. So let's see how this works. So this is the 2 equations we are left with after the phase transition when the dark sector is confined. And as said, now the thermodynamic functions might still depend for a temperature parameter for a while, for a moment, until the states are fully freeze out. But at the same time, then they depend on the global dynamics and their self-interactions. So already to parameterize the energy density and the pressure, then we need the the number densities for all the global states we are including. I was saying I include 3, so here we have 3 variables plus the temperature, at least until the end of the pre-result. And then we have also the standard model energy density as before. So in total, we have 4 variables and only 2 equations. So we need more equations to solve the system. And those equations are given by Boltzmann equation for the number densities of global states. They look like this. So the different global states have different decay with to standard model degrees of freedom. And in principle, entering these equations, we have a tower of infinite global self-interactions. Another question is, so where can we truncate this series of interaction? Do all of them play an important role in our analysis? Unfortunately not, because the information we want to extract at the end of this exercise is how much dark matter are we left with, and what is the temperature of the standard model sourced in this scenario. And what the important information then is encoded in the number density of the odd global states, because remember the odd states are those that do not decay to standard model particles, or I mean they decay but with dimension 9 decay rate scaling with lambda to the 9. So what we really want to keep are number changing interactions that change the numbers of even or odd globals, and also so 3 to 2 is the lowest order, and also 2 to 2 interactions with number changing features. So this is the form that those interactions take, and they are controlled by some effective cross sections, so average cross sections. And unfortunately, for those cross sections, even in the SU3 case, we not always have enough lattice inputs, so we then use some large N expansion results or naive dimensional analysis. The important information about the cross sections is that, of course, they go inversely proportional as the confinement scale. So if the confinement of our dark sector appears at so earlier, so at higher energies, then we will have less efficient self-interactions among the globals, and probably a faster freeze out. So we can solve the equations numerically also in this case, and so this is so we can really observe the freeze out of our global states. So in blue we see the lightest even state, and the dotted line is the equilibrium distribution, which is followed as long as the 3 to 2 interactions are present, and as soon as they are suppressed, then the distribution of the even states freeze out, they say, so it doesn't follow the equilibrium distribution anymore, and a chemical potential develops. So for the odd states, which are illustrated in red, this implies that okay, we now have a chemical potential, but the 2 to 2 interactions are still active. Therefore, the distribution of the odd states keep following the new equilibrium distribution with the chemical potential until at some point also these 2 to 2 interactions are inefficient and all states freeze out. At this moment, we can forget about the equilibrium and the notion of a temperature, and we continue the analysis only with the number densities as variables. And yes, I was saying we have stronger interactions at lower confinement scales. And this would mean that the full picture is shifted to the right. So it takes more time because, sorry, the x-axis is given by temperature, and the temperature is decreasing here because time is increasing. So it will take more time to freeze out, and taking more time to freeze out also means that this more or less constant density we reach at the end will be at a lower scale, implying also that the amount of odd glue balls will be lower, and the odd glue balls, remember, might populate the dark matter. So going to smaller confinement scales would imply that we go to lower Redick dark matter abundancy. So going back to the full picture now, we also understand how like the right part of the plot is obtained, and now we would like to constrain this scenario. So we already have an intuition for what happens if we modify the confinement scale, and also notes that if the confinement scale is smaller, then we reach the critical temperature later. So not only the freeze out takes longer and therefore the relic abundance will be smaller, but also it will start at lower energy. So it has quite a large impact. On the other hand, also this moment where the standard model sector starts dominating depends in a non-trivial way on how the confinement scale and the scale of new physics relate to each other, because this is given by equality of the decay width with the decay width and the upper rate. So we can already see that we might have from dark matter abundancy, we might already have a maximal confinement scale that is allowed, because otherwise we might have too much dark matter if we go to too large confinement scales. And another maximal or another upper bound for lambda could be given by finding what is the lifetime of the stable global states, which are the odd ones. So just analytically computing one over the decay width, we find another upper bound for lambda. And then, as I was saying, so extracting the temperature in the standard model sector, once it starts dominating, we then also find a lower bound for the confinement scales. And now our parameter space is closed, and this is how it looks like. So as said, the abundance of dark matter sets an upper bound for the confinement scale. And then we have another upper bound by the lifetime of the stable glue balls, which is given by indirect detections with some uncertainties. And on the other hand, as a lower bound, we have the reheating temperature of the standard model, which is bounded by Big Bang nucleosynthesis observations that require it to be larger than 4 megaelectron volt. So this picture illustrates an open parameter space, because this white region, which is the allowed one, is there, but at the same time is also quite a narrow one. So now the conclusion one could draw, looking at the picture, are different depending on what is your orientation with respect to inflation. So if sorry, don't know what happens. If we want to be very optimistic, well, the good news is that we have found a quite generic framework, and that can link the end of inflation to the advent of the standard model, with a generic non-Abelian dark sector that satisfies all requirements we have from the phenomenology point of view. On the other hand, another fair point is that there are a number of theoretical uncertainties in our analysis, and that are not very well under control. And the results, also given those uncertainties, is still a very narrow parameter space. So the question is if the parameter space would remain open once we do the analysis with more information about the global states. And all in all, I think with the safe conclusion we can draw is that we need more non-perturbative information. And in general, it is interesting for early universe physics to have more inputs from lattice or maybe other techniques. And in any case, whatever is your idea, then now I hope I convinced you that, and this transition period from the end of inflation to the advent of the standard model is a very crucial one, and we should at some point be able to explain it, to cross-check the validity of any model before it, and also it is full of interesting physics. So thank you for your attention. I'm happy to take questions.
Okay, thank you for the very nice talk. Any question from the audience? Please unmute.